I'm sort of a little removed from the central themes in this meeting. I'll try to avoid, jargon which is coming from our community, and I suppose there is. I've sort of managed to squeeze in the words thermalization and many-body in the title to sort of find my place here. Okay, so the brief outline, and I'm really happy if I can cover the first part in some detail, which is background, which is to try to show you what people in our sort of turbulence and people who work with these Euler-Navier-Stokes type equation, what we mean by thermalization and how inviscid or zero viscosity equations thermalize, and then I will talk a little bit about how such thermalizations can be suppressed, and the last bit is continuing on Shubhra's talk on Monday to try and sort of tell you a little bit about some recent results that we've had making use of such solutions. So let me begin. The first part of my talk is really to sort of give a quick summary of some old work, which begins with Andy Maeda's paper in 2000, who showed how sort of inviscid equations, well, the fact that inviscid equations can actually thermalize, and some later work done by my collaborators, Frisch, Nazarenko, Matsumoto, and a year or so ago with my former postdoc, Divya. All right, so what's the context? What's the sort of setting in which we would like to think about such questions? So firstly, in this talk, we are going to concentrate on partial differential equations for inviscid hydrodynamics. So there is no viscous term here. This is the standard one-dimensional Berger's equation. Some of you might be familiar with versions of this which sort of shows up in cosmology in what's known as the Zeldovich approximation, or more commonly in condensed matter physics as the KPZ equation. So in general, there are sort of, to solve this equation, there are sort of standard tools theoretically and numerically, typically in the small viscosity limit, which could be the Hopf-Kohl method, the Fourier-Lagrange representation, the convex hull construction, and numerically, going back to the work of Massimo Vergasola and Alain Nulles, we know we have well-defined ways to actually solve this equation. And the standard features, and we'll come to this in a little bit, I'm just sort of giving a quick introduction as to what these equations could look like. So the standard features that we now seem to identify, and here are references to some review papers, is the fact that the 1D Berger's equation indeed has finite time singularities. There is a T star when the complex singularity hits the real domain, and there is anomalous dissipation even in the absence of viscosity. Things get dissipated in this sort of shock solution. So the analog, or the more sort of important problem, is that of the three-dimensional Euler equations, which sort of looks exactly like the Berger's equation, except now you have pressure and it's in 3 dimensions. And here, both the issue of the finite time singularity, which is one of the sort of key central questions in mathematics, it still remains open, and the issue of anomalous dissipation or weak solutions, and I explain this in a little while, also is a sort of open question. So in the first bit, what I'm really going to talk about is how does one solve such equations on the computer? And the way one does this is through what is known as a Galerkin-truncation. So essentially what we do on the computer is we take the partial differential equation, we Galerkin-truncate it, and I'll give the formula in a bit. I'm just giving the schematic for the moment, which is we project it onto a Fourier subspace with a finite support. That allows phase space and energy conservations, and eventually the long-time dynamics lead to thermalized solutions, which are nothing like the shocks, for example, that you saw in the Berger's equation. So more technically, what we do is we take the inviscid partial differential equation, we define a projector which projects the velocity field onto a Fourier subspace which spans up from wave numbers minus kg to kg. So that is your bound, that's known as the truncation wave number. And then you obtain an equation which looks like the first equation, but it's not. That's because you have this projector sitting in this equation, which makes sure that you project it into the subspace spanning kg and minus kg. So what goes on when you do this? This seems to be a sort of naive sort of thing to do. What happens is, firstly, you break integrability, and then this equation never converges to the inviscid partial differential equation. So what you have is, what I showed in the movies, maybe we can start it again, is I'm showing both in black the solution to this equation, in red the solution to this equation, and you see the black has the familiar shock solutions, whereas the red ones seem to, in a very short time, seem to thermalize and show chaotic solutions, which leads to, and in a bit we'll see what the consequence of this is. The important result, which was given by Bardos and Tadmor, short while after our work, was that there is no way that this equation converges to the first equation, even in the truncation wave number going to the infinity limit. And that has to do with the fact that you are breaking integrability when you do it. And the consequence of this thermalization, and this is my sort of definition of thermalization, if you will, is the fact that you end up getting an energy spectrum or the distribution of kinetic energy in the various Fourier modes. In the original equation, you would have got a k minus 2, which is just because of the fact that there are shocks sitting in the solution, whereas once they thermalize, you end up getting an equipartition spectrum, which in 0 dimensions is just k to the power 0. So that's flat line. All right. Sorry. There's the advantage, just to say that the two are different equations. And I'll look at that advantage in a bit because, okay, so if your question is, why do people care about this? That's because it goes back to earlier work by Crichton and T.D. and others. Often you would have expected that in the limit when Keiji goes to infinity, and you pass to the Galerkin limit, maybe there are certain things that you're going to prove. And I'll show that in a second. Yes, sir. Yes, it is volume preserving, and so the phase space is conserved, which so you can bring in all the machinery of Gibbsian ensembles and Liouville's theorems, etc. Okay, very good. Sorry. Yes, actually the first 3 moments of U are preserved, the rest are broken. Maybe I can show it in the Blackboard a little later. The first 3 are, the first and the second are easy to show. The cubic moment is a little more complicated, but the others are broken. In the original case, you had all moments of the U which were conserved, all right? Okay, sorry, I'm going a bit slow. All right, so the question is, do we understand how such equations thermalize? And this was sort of an early work from a few years ago, and there are a few other references which sort of explore this, but I'll give you a little flavor as to what's going on. For example, if you begin, and this is at some time point 2, you begin with an equation which has an initial condition which after some time gives rise to this structure. And very soon, for example, here you should see a shock appearing. The minute the shock appears in the truncated system, what you end up having are these localized bulges. And these bulges, for embarrassing reasons, were called tigers in our paper. And what you see is that these tigers, or these sort of first signatures of truncation, show up at resonance points with the shock and where there is a positive gradient. So this is sort of, and eventually, as we saw in the movie, these guys, the blues, the red is the entropy solution, the untruncated. With the blue, you eventually see that they sort of percolate or spread along the ramp, and they end up essentially thermalizing the whole system. So what we now know with reasonable certainty, and I'm not going to derive any of these results, is that these early bulges that we saw in this plot, one can do a reasonable scaling analysis of these early bulges, and what we have now are very good predictions as to what the amplitude and the width of these bulges are and how they depend on Keiji. There are power laws everywhere. And also, more recently, what Divya was able to show was the fact that we do have a suitable prediction as to what the onset of thermalization is. As you can see, these structures are tiny, so at early times they shouldn't play a role at all. It's only under evolution that these bulges become big, they spread, and one can then sort of have an estimate as to the onset time in which the solution really starts looking chaotic and thermalization. So that's sort of the background in which I want to sort of present more recent results, but in case someone is more interested from the point of view of turbulence, etc., I should remark, and this sort of addresses Dibyendu's question a little bit, as to why people at all worried about these equations. And historically, ancient history, people like T.D. Lee, Edward Hoff, Crichton, etc., used such truncated systems a lot to derive certain results for Navier-Stokes or hydrodynamic turbulence. And more recently, along with Itamar, Uriel Frisch, Anna Permialov, we were able to show that one can generalize these operators to actually obtain d-dimensional hydrodynamic equations. And those seem to have rather interesting connections with more sort of conventional problems in turbulence, which have to do with intermittency and irreversibility. So this sort of brings me to the focus, the first part of the focus of my talk. And the question that, this is work done by my student Sugan. And the question is really, should we and can we suppress thermalization? So I want to address the should we question first. And then, as you can guess, the answer to the second part is yes, of course. But maybe it's good to actually understand, should we suppress thermalization? So for this, I'll give you two reasons. The first goes back to that ancient problem of Euler equations and finite time blow-up. So, a description, a very nice write-up is by Pfefferman in the Clay website, which describes what I'm going to say in about 2 slides. And it's the following. So we know that at least certainly up to some time, the solutions of the three-dimensional Euler equations are analytic. There could be complex singularities, but they're certainly not hitting the real domain. So one way to actually measure this is to essentially measure what's known as the width of the analyticity strip, essentially how far away are these complex singularities from the real domain. So it's a little painful, but one can show that the Fourier transform of such analytic functions essentially have an asymptotic behavior which goes as exponential minus 2 delta k. So all that remains, a restatement of the finite time blow-up problem, is essentially to ask the question, in finite time, does this delta actually go to 0? For the Burger's equation, we know, for many years that the answer is yes. That's what gives rise to the shock. So the question then is, numerically, what one can do is integrate the Euler equation in time, and you can only do it through Galerkin-truncation, calculate the energy spectrum, measure this, and you end up getting delta. So it's, in 2019, it's worth asking, why is this problem still unsolved, and why do we write research grants for solving this problem? The answer to this is the fact that things thermalize. So this is one of my sort of favorite papers from Marc Brachet in the mid-2000s, where he actually integrated the Euler equation, and lo and behold, this is the energy spectrum at different times. You see that k-squared equipartition spectrum creeping in. That's because the equations have thermalized. So there is no way that you can measure delta up to any finite length of time, and no way you can sort of, essentially, you measure delta from semi-log plots. This is what people do. This is results of Bustamante and Brachet. There are plenty of papers on this. This is the last one that I'm familiar with. You measure the slope, measure delta, plot delta as a function of time. Unfortunately, thermalization has kicked in. So from around this point, you cannot measure delta anymore. And so you cannot conjecture numerically whether delta would have gone to 0 or not in a finite time. Although Mark and Miguel suggest that at least at early times, this seemed to go down exponentially. But there are results from Bob Kerr's group where thermalization was even stronger, where the results are quite different. There's another reason why we should suppress thermalization, and this is the only bit where I'll talk a little bit about turbulence per se, and this has to do with the problem of anomalous dissipation in turbulence. And the problem, very simply, is the following. If you measure the energy dissipation rate in your wind tunnel or in your computer Navier-Stokes simulation as a function of Reynolds or the inverse of viscosity, what you end up getting is a saturation of the energy dissipation rate. So at some point, even when the viscosity goes to 0, there is a finite energy dissipation. Where is this coming from? And this goes back to the famous conjecture of Onsager in the 40s, who pointed out that if the Hölder exponent for the velocity field in the Euler equations was less than one third, you will necessarily get a dissipative solution. The problem again becomes, and there is more recent work, and I've sort of listed various people, especially Skelehidis' work in the last couple of years with Buckmaster and Peter Constantine, are absolutely phenomenal in this field. But the problem is, numerically, there is no way that you are going to see the weak dissipative Euler solutions because energy is conserved and things thermalize. So the question that Sugan and I asked is, can we actually prevent thermalization? Essentially, without adding any viscosity, can we actually obtain dissipative solutions to these Inviscid equations? And the answer is yes, and I'll sort of sketch out the procedure that we are using, and that's why I'm rather happy to be speaking here, because this is quite recent and it's the first time I'm talking about this. So as you recall, this is your standard Galerkin-truncation. We obtain what are known as purged solutions, which is exactly the same as the Galerkin-truncated equation, but with an additional constraint, which is we set these velocity fields, these Fourier modes of the velocity field to 0 at discrete times. All right? And we make an ansatz, and then we actually try to firm up this ansatz, and we say, let's choose this time scale tau, which is the interpurging time, as some kg to the power minus alpha. Remember, 1 over kg is the only small parameter we have in this problem, right? And we choose a purging wave number. The wave numbers, the boundary layer bit close to kg, where we actually set modes to 0. We choose that boundary layer as kg minus kg to the power beta. So schematically, all that this means is, if this is my Fourier space, then every interval tau, the small boundary layer, I just erase it out. And then till the next time interval, I allow things to evolve. So the question really becomes, how do I choose this alpha and beta? So again, keep in mind, we are after dissipative or weak solutions where the energy, the rate of change of energy is negative. It's going to dissipate. In the truncated case, this is strictly equal to 0 by theory. So what we do is, what this allows us is that we essentially lose a little energy between these wave numbers kp and kg, and the rate of loss, because this is done every time interval tau, will essentially be just this chap divided by tau. So what we have now, and I'm not going to give the full calculation, what we have calculated is the behavior at this boundary layer, the functional form of the truncated solution here, which we get rid of, and that tells us that given a certain beta, we either lose an energy proportional to kg beta minus 2, or we lose an energy proportional to kg minus 5/3 for beta greater than 1/3. Secondly, we can actually go ahead and calculate the rate of energy loss. And for convergence to happen, this rate of energy loss has to be independent of kg as kg goes to infinity, right? That would be the definition of whether our purged solution converges to the untruncated one. And we find a rather interesting constraint on alpha and beta, that they have to be order 1 for this to happen. So the point being that we need alpha and beta. This was our ansatz. Our sort of semi-rigorous bound suggests that alpha and beta satisfy this relation, and beta has to be strictly greater than 1/3. So does it actually work? So here, what I plot is the Galerkin-truncated solution is in blue. The entropy solution is in black, and the purged solution is in red. And I'm showing results for 2 values of alpha and beta. And what I can point out, you'll see that this, which satisfies our bound better, seems to do a better job. So let's look at the solution before we make this convergence more precise. So as you can see here, modulo the Gibbs oscillations, which is independent of the problem, the red and the black line seem to converge arbitrarily close to each other. How close is the convergence? I'll show you in a second. So this then is a reasonable sort of, you see already the truncated one has thermalized, whereas our recipe for obtaining the dissipative solution seems to still hold. Sorry. We use the Vargasola technique, which is the fast leisure method, which is essentially you construct the convex hull and you integrate it in time to get the exact solution in the viscosity going to 0 limit. It's a numerical technique, but it agrees well with the Fourier Lagrange representation. Okay, so here, okay, this is not greatly visible, but that's probably good. So red and black, there is still some discrepancy when you don't choose alpha, beta, satisfying the bounds that we have. But when you do, and you have to probably trust me here, you see that the black and red curves are coincident. So what we do is, as a quantitative measure for this, we calculate the difference, the relative error between the total energy of the purged solution and the entropy solution. So here, for example, we are plotting the total energy as a function of time. The black line here is for the entropy solution. The different red curves correspond to different choices of alpha and beta. But happily, for the right values of alpha and beta, you find, at least to the eye, the purged energy and the entropy energy behave exactly the same way. So this is a nice way to get a dissipative solution from an Inviscid equation. So we went ahead and actually calculate the relative error as a function of Kg for this curve, and we find that the agreement is less than 0.01%, which I think is pretty good. So what you can do, you can make an even more quantitative error estimate, where you calculate essentially the L2 norm of the difference between the purged and the entropy solution. So this is really going to be sensitive on how much our numerical recipe actually works. And what we find, again, as a function of Kg, this seems to scale, it seems to go down a little faster than 1 over Kg, which is good news, of course. And you find, again, that it's less than 1% for the larger values of Kg that we've used. So in summary, for this part, what we do, what we think, what Sugan has achieved is he has been able to obtain a recipe to obtain weak dissipative solutions. The good thing is, if you kept a track of the values of these exponents, the good thing is that there is a minimal loss of resolution. So if you're doing a numerical simulation with the largest wave number 20,000, you just lose about 200 wave numbers. So that's peanuts. And secondly, this method is sort of trivial to use for the Euler equations. And right now, Sugan and I are working on the Euler equations to try and see if we get, if the dissipative solutions are of the sort that Konstantin and others have predicted. Okay. So then in the remaining sort of 12 minutes that I have, I will sort of take off from where Shubro left off in the last, in his talk on Monday, and change gears. Because we began with showing how Inviscid equations of hydrodynamics thermalizes. Then I made the case that it might be useful to get rid of thermalization. And now I'm going to switch gears and say that if you can't get rid of thermalization, it's best to make hay while the sun shines. So let's see what we can gain from actually living with thermalized solutions. So, so this is sort of in archive. This paper is in archive. And since Shubro gave a background to these sort of problems, I won't labor on the point, except to say that the thrust of this is to try and ask what is the classical limit of these OTOCs that Shubro was talking about, and secondly, what is the temperature dependence of the Lyapunov exponent. And we'll see that the truncated Burger's equation, again, the Bandhu sort of seems to be a useful tool to actually study this. Okay, I don't have time. So essentially, let me sort of digress and sort of just take it up from where he left off. Shubro had discussed this question of the classical Heisenberg spin chain, and this is a paper written by many of us who are in the audience, especially Abhijit and Shourish, who did many of the calculations. There's Abhishek, Anupam, Shubro, of course. So what we did was, just to refresh your memory in a slide, was we took the classical Heisenberg spin chain at infinite temperature. So that's the Hamiltonian, and we have the spin precession dynamics. And what we had calculated was to make two copies of this chap. One of them is slightly perturbed, one spin at one position, x equal to 0. The perturbation is so small that you don't see it on the slide, partly because it's the same figure that I've used for both the spin chains in this case. And then you sort of measure the decorrelation between these two spin chains, and you get this light cone behavior. The fact that the perturbation, so there's a Lyapunov exponent associated with the growth of these perturbations, and there's a sort of butterfly speed associated with the spread of these guys. So the question really becomes that is there a more nonlinear sort of equation that we are more familiar with where we know things are chaotic? So the first thing that, given my background that comes to me is turbulent flows. Now that's much more of a problem. It's driven dissipative. So the other thing that, of course, comes to my mind is why not look at the partial differential equation of the Burgers variety? And let's look at the Galerkin-truncated version of it. The good thing, as we saw, was the fact that this thermalizes, and this red is the solution of the truncated equation. And essentially, if you look at, and you can actually go ahead and measure, actually before us, Marc Brachet did it with Pablo Minini, is to actually look at the distribution of the velocities, and you find the standard Gibbsian behavior. So the question that, so the strategy that we employed to sort of find the classical limit of this OTEOC is the following. We solve the truncated Burgers. We allow it to evolve this for a long time. I should point out that the chap who did that is sitting there, Dheeraj Kumar. He's heading to Paris for his PhD in a few weeks. So what Dheeraj did was to solve the Galerkin-truncated Burgers equation, ran it for a while, till it thermalized, till it had these Gibbsian distributions. And then he made a copy of it, and he called that VA. Then he took another copy, but there he added a slight perturbation at some wave number Kp. All right? So the two systems are now identical, except one of them has a tiny small-scale perturbation. And then just as we did for the Heisenberg spin chain, what we measured was the decorrelator. Now in Fourier space, that's the natural sort of space to work in here. And we measured the decorrelator, which is just the difference between the two thermalized ensemble, A and B, one of them being slightly perturbed. That's some small wave number. So just to tell you exactly how this was done, so theoretically, one can write down an equation for this decorrelator in the Burgers problem. That's the easy and useful part. It's still a nonlinear equation, so we are able to solve the linearized form, which of course, when you linearize, there are some approximations which one validated with numerical results, and the nonlinear form one can solve numerically. And the expectations from our theoretical calculation in the linearized version of this equation and the nonlinear form is essentially that at short times, you would have an exponential growth, and at long time, this would saturate with a value which is just the modal energy. Ng is the number of Fourier modes which we retain in this problem. All right? The other approach is, of course, to look at direct numerical simulations. We can solve system A and B as we were doing, and then at every discrete time intervals, actually calculate the decorrelator between these two chains. So here's a plot of delta K, which has data from the direct numerical simulations for different values of wave numbers, the linearized form, and the full nonlinear form. What you see is, I would say, a pretty good agreement for the exponential part of this growth. And then you see it saturates, and this saturation value is exactly the same as E over Ng, as our theory predicts. However, the linearized form never saturates. You actually need the nonlinearity to saturate the decorrelation to the modal energies. And the question, so from the sort of exponential early growth, and again, DNS means solving the full sort of equations and then calculating the cross correlator. So the question really becomes is to fish out the Lyapunov exponent from these short time bursts. So this is a semi-log plot. So you see that it is indeed growing exponentially. So Dheeraj sort of used various fancy techniques such as local slopes, etc., to calculate lambda. And the question that one asks is, what does lambda depend on? Does it depend on the perturbation wave number, the wave number at which you measure the decorrelation? Does it depend on the number of degrees of freedom that you have? Because this is an old sort of, chaos question, right? I mean, how does the degree of chaos span with system size? And does it depend on temperature? So just to recall the sort of the famous quantum bound being that lambda is bounded from below by the temperature. So the analytical prediction from the linearized form of this equation was that the Lyapunov exponent should scale with the number of degrees of freedom and square root t. And this is sort of consistent with the work of Kuchan and others. And lo and behold, so this is many, many lambdas that we plotted together as a function of temperature. I should point out that in the Burgers problem, the good thing is changing temperature is very easy. All you need to do is change the initial amplitude of the initial condition, right? Because since energy is conserved and you can relate energy with temperature, thanks to the equipartition ideas that we discussed in the beginning of this talk. So to change temperature, all one does is to change the amplitude of the initial conditions, right? So what we do is we plot lambda for different NGs, for different perturbation wave numbers, for different amplitudes of perturbation, and happily they fall on a rather nice scaling, which is NG square root 2, exactly what the prediction that we have. So this is one of the sort of early results this year from to sort of show in a microscopic model, but more importantly, a model which is of a hydrodynamic nature, right? We began with a PDE, an Inviscid PDE, which is completely well respected, at least in my community, for studying systems of hydrodynamics. So with that, and I'm sort of also out of time, let me sort of summarize what we had for this part. So this is really what we think are the first set of results for the classical analog of the quantum OTOC problem, and the temperature dependence of the Lyapunov exponent in this continuum model. And this is sort of consistent with the results that Shubro was pointing out, his work with Roderick and Biliteski, as well as Kurchan's conjecture. So I just want to leave with the final sort of perspective. So right now with a friend of ours, Vishwanath Shukla, Shubro and I are looking at testing these ideas in the two-dimensional Gross-Pitaevsky model to sort of see what the scaling for these lambdas. I think Shubro and others have some predictions for how the temperature dependence should be across the BKT transition. So for the moment, all I can say is that it seems promising, the use of the truncated Gross-Pitaevsky equation in 2D. Okay, so I will leave it there. I still have a couple of minutes for questions. Thank you. Yes, Manas. Ng is the number of modes that we have. It's the same as kg. Shubro doesn't like kg because it's dimensional, so I choose it. I use it as the number of modes.
But I mean, if you increase kg,
yes,
in some sense, you are. I mean, aren't you approaching the integrability little more? So you would expect Lyapunov to go down, no, or it doesn't happen that way, right?
This was the great result of Tadmor and Bardos, which I pointed out towards the beginning. The fact that for these equations of hydrodynamics, kg going to infinity limit does not converge to the untruncated equation.
Sure, but at least it would be slightly more. No, it's just
slightly. Okay. It still thermalizes. Okay. So in the work with Uriel and others, the original Tyger paper, we went up to kg, I forget, 40,000 or something. So it's like 2 to the power 18 kind of simulations, and it's exactly the same behavior. The scaling laws follow of the width bulge of these Tigers and the thermalization time. No, it doesn't. It's just because as long as you have a kg, you are breaking the integrability of the system.
You're saying more the kg, more Lyapunov.
Well, what we are saying is that the degree of chaos of Lyapunov is a good measure of that spans with the available degrees of freedom. But that is something that a lot of us, I think, believe for a long time. I mean, I'm not aware of too many results on that, but that's not the main surprise. I mean, that's part of the surprise, but the main might be the square root temperature.
I have one naive question. When OTOC is defined as the square of commutator, its classical limit is the square of the Poisson bracket. Right. So with whatever the things we are speaking about the classical limit, what was the?
So the rigorous. So I just sort of went through that slide a little. Maybe I can discuss this later. But for the Heisenberg spin chain, we actually showed exactly how the correspondence works when you go to the Poisson bracket. In the case of the truncated burgers where things thermalize, I really don't need to worry about that. I take the definition of the decorrelator which we get from using these Poisson brackets, etc. Because for these hydrodynamic systems, it's much harder to write down the Hamiltonian, etc. And I use the definition of the decorrelator which emerges from this reading. And so I just look at that decorrelator.
So you showed us the Maxwellian for the velocities, right? I mean, in the thermalized state, I mean, you showed us that the velocities have a nice Maxwellian distribution.
Yes.
Now the question is, did you also measure the spatial correlation lengths?
For these velocities?
Yeah, well, I mean, in the thermalized state.
In the thermalized state, no. I think Brachet's group did it. And I've not seen that paper, so that was one of the reasons I didn't do it. Because so Mark told me that they were measuring.
It would be just sort of an additional information, right? Because,
exactly. No, we haven't. So we had just looked at the distribution of the fields, but not the correlations. In Fourier space, but it's true that the energy spectrum is the Fourier transform of the two-point correlator. So that's an indirect way to see that it's a white noise kind of behavior.
Sankar.